Hello again, everybody, and welcome to another Geo-Institute live stream. You missed me last week. Well, maybe you didn't, but I am back. I'm Brad Keeler, director of the Geo-Institute, here to welcome you to episode 4 of the Keller Sustainability Series. If you are here and just by chance you don't know anything about the Geo-Institute, after you watch this here live stream today, you should head over to geoinstitute.org. There you will find out lots of things, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. If you like what you see today, and I've heard Alessandro speak before, I feel like you're going to. I will stop short of guaranteeing it because anything could happen, viewers, but I think you're going to. You're really going to like this today. As I mentioned, it is part 4 of the Keller Sustainability Series. We will have one more episode, and we will tell you a little bit about that at the end of today's broadcast. But if you do like what you see, I never told them what they should do. You're supposed to click like, subscribe, and get notifications. And if you do those things, we will let you know every time we post something to the YouTube channel. One more administrative task for you. When you are listening to Alessandro's presentation and you think to yourself, I have a question about what he just said, you can put that question in the chat box to the right of the window where you are watching this, and we will endeavor to answer it after the presentation. Now, here to introduce our speaker today, tell you a little bit more about Keller and about the series in general, is business development man extraordinaire from the left coast of America. It is Tim Avery. Tim, welcome.
Thank you, Brad. It is my great pleasure to introduce Dr. Alessandro Rotta Loria. He is the Louis Berger Junior Professor at Northwestern University, where he directs SOIL, the Subsurface Opportunities and Innovations Laboratory. He is the co-founder of GEOG, an engineering design and innovation firm specializing in underground energy solutions, and is the co-founder of Enerdrate, a company developing the world's first geothermal panel. Alessandro's expertise is in geothermal energy, underground engineering, obviously geotechnical engineering, and geomechanics. Alessandro is co-author of the book Analysis and Design of Energy Geostructures and has published 2 book chapters, 2 patents, and over 100 publications in scientific journals and conference proceedings. His work has been featured by international media, including the New York Times, Washington Post, Financial Times, Scientific American, CNN, BBC, Forbes, and Bloomberg, and has been presented at such venues such as the Seoul Biennial of Architecture and Urbanism. As a result of his work, Alessandro has been named World Innovator Under 35 by none other than the MIT Technology Review, and has been included in the 40 Under 40 list by Crane's Chicago Business. He's now in Turin, Italy, the epicenter of Western cuisine, and it is high praise indeed that he finds the local Chicago tomato sauce pie to be so darn delicious. With that, please welcome Dr. Alessandro Rotta Loria, who will present Energy Geostructures, underground constructions providing renewable energy. Take it away.
Thank you very much, Tim. So I will share the screen. That you should now be able to see. So good morning, good afternoon, and good evening, everyone. It's a great pleasure for me to be here. And as a matter of fact, before I start, I would like to sincerely thank Brad Keeler from the GI for the invitation to deliver this talk, and of course, Keller for this wonderful opportunity. I'm very happy to be here, and I'll look forward to interacting with all the audience at the end who might have questions. So in the following, I will essentially expand on the science and engineering of an emerging technology called energy geostructures that essentially consists of underground constructions providing combined structural support and renewable energy supply. This is the result of several collaborations that I had over the years. As a matter of fact, the results that I will present you really are the result of many efforts, and of course, without these people, I would not be here talking. So I gratefully acknowledge also all their contributions. Now, without further ado, the presentation today will be divided into four main parts. I will first kick off by talking about energy-related challenges in urban areas. I will then present one of the possible solutions for those challenges, which are energy geostructures. Afterwards, I will talk about some fundamentals behind the analysis and design of energy geostructures, and I will conclude with some application examples. Now, let's start by talking about energy-related challenges in urban areas, and why am I going to focus on urban areas? Well, because despite urban areas and cities occupy only 2% of the world's surface, they host up to 50% of the world population, account for 75% of the global energy consumption, and up to 80% of the global CO2 emissions. So essentially, the message is that, of course, human settlements can span across different territories, but most of us live in cities. And as a matter of fact, recent statistics indicate that every month, a new city of London is constructed around the world. And so really, most of us live in urban areas. Urban areas consume tremendous amount of energy, and due to the customary reliance of non-renewable energy sources, they are a big contributor to global warming and climate change. Now, despite the current interest in the electrification of our world, if we break down the energy budget, the energy bill in our buildings, we can realize how, depending on the country, from 40 to 80% of the energy we consume is actually used for space heating and cooling and hot water production. So if we take as reference the city of Chicago, we can see that approximately 45% of the energy used in buildings is really used for these applications. Now, of course, electricity can be used to produce heating and cooling, but as a matter of fact, if we were able to source directly thermal energy instead of converting electrical energy into heat, we would have much more effective applications. Now, a possible way to do this is through the harvesting of geothermal energy, the most abundant renewable energy source available on Earth right after solar energy, that I'm used to introduce by showing these two posters that were designed by Frederick Charles Herrick for the London Underground. And essentially, the message of these two posters is that when outside, like at the ground surface, is hot and sunny, temperatures are cooler below. And on the other side, when at the ground surface is cold, it is warmer below. So really, the key message of these posters was that if you consider it from a broader perspective, that the temperature in the ground beyond a few meters of depth is relatively constant throughout the year, being warmer than the ambient temperature during winter and cooler than the ambient temperature during summer. And so essentially, all shallow geothermal technologies, or geo-exchange as we call it in the US, resorts to this fact, resorts to the fact that temperature in the ground a few meters of depth is constant. And this principle essentially allows us to source this heat for the heating and cooling of buildings and the production of hot water. Here you have data that have been measured in the ground around the world. And really, you can see how the temperature remains relatively constant with depth. Of course, there is the geothermal gradient of approximately 3 degrees Celsius per 100 meters of depth. But if you consider the first, let's say, 100 meters of depth, you typically deal with relatively constant temperature. Again, if you neglect the first 4 to 5 meters, where you do have an influence of the surface climatic conditions. Now, this fact is valid everywhere on Earth, irrespective of where you are. Of course, if you are close to volcanoes, you are going to have a more significant geothermal heat. But really, the fact that the temperature is constant is true everywhere. Now, everywhere. But so if you instead consider cities, so instead of rural areas, now you consider cities, you can see how around the world, the temperature, there typically is an offset in the temperatures with depth. And this is due to so-called subsurface urban heat islands, a phenomenon that essentially consists in an underground climate change associated with average temperature rises in ground temperature of up to 2.5 degrees Celsius per decade, which put into perspective is higher than the rate of surface global warming. And this is due to the fact that all underground structures, such as building basements, parking garages, subway tunnels, train tunnels, and so on and so forth, continuously reject heat in the ground, no matter how well they are insulated. And so this is really causing an increasingly ubiquitous phenomenon. And really here the message is that on top of having geothermal heat everywhere on Earth, when we are in urban areas, we also have substantial amounts of waste heat that we can harvest, and we can harvest with geothermal technologies. Now, later with this presentation, I will show you how we can do that. But before, let me expand a little bit more on this phenomenon of subsurface urban heat islands, because as a matter of fact, it causes various deleterious issues for urban areas. First of all, it represents an environmental issue because rising ground temperatures affect seed germination and plant growth. It also represents a public comfort and health issue because, as a matter of fact, there are hundreds of cases worldwide of people feeling thermal discomforts who, for example, use public transportation systems, subways, but also people who suffer from heat-induced diseases such as stroke and asthma and others. And on top of that, it also represents a transportation infrastructure issue because the rails of trains traveling underground can often be at the onset of buckling due to the very significant temperature that can be found underground, at least in some underground environments beneath urban areas worldwide. And so urban heat islands, as a matter of fact, are an unwanted phenomenon that characterizes most urban areas worldwide. Really, as soon as we build a building, some heat will dissipate into the ground, and so we will generate temperature anomalies. Now, as civil engineers and geotechnical engineers, we know that soils, rock, concrete, and system thereof, so essentially the backbone of the subsurface, deforms and subjected to temperature variations. Materials such as concrete and various soils expand when heated, but some other types of soils, depending on the stress history, stress state, and other variables, contract upon heating, and this phenomenon is often called thermal collapse. And so, although over the years, all the previous aspects about subsurface urban heat islands have been studied in detail, so the environmental aspects, public health and comfort aspects, and transportation infrastructure aspects, before the research that I carried out with my group, there was very limited knowledge about the influence of subsurface urban heat islands on civil infrastructure. And so here now we'll open a little parenthesis to essentially provide you with one additional reason why we should harness this waste heat. And so the study that we'll present you, as has been introduced by Tim, has been featured by several media across the world due to its wide implications for civil infrastructure, because as I will show you in the sequel, it can represent on a case-by-case basis an issue for the performance of civil structures and infrastructures. But let me be more specific. So essentially for this study, because of geographical proximity, together with my team, we chose to use the city of Chicago, and specifically the Chicago Loop District, as a case study. The Chicago Loop District is actually the second densest district in the US after Manhattan in New York City, and is renowned because it's constructed essentially upon layers. So there are a myriad of underground environments, such as building basements, a system of pathways, parking garages, subway tunnels, train tunnels, and also a very intricate network of freight tunnels that are currently not open, but still in use by a number of companies. Now, the local hydrogeology of Chicago is also very interesting because it's quite diverse. It presents both fine-grained soils and coarse-grained soils, and the fine-grained soils that are present at the site can be both normally consolidated and over-consolidated. Now, as a part of this work, what we did was essentially to turn the Chicago Loop District into a living lab. And for this, we deployed hundreds of wireless temperature sensors, both above and below the ground, really with the aim to measure temperature, especially in underground environments, and quantify, seemingly for the first time, the intensity of the subsurface urban heat island beneath Chicago and the impacts on civil infrastructure. Here we have an idea of what the sensors look like. Essentially, they are as large as an egg, and they can be easily attached anywhere and also embedded into the ground to measure temperatures. And so what we're able to do with this sensing network currently is to gather approximately 20,000 temperature data per day that in turn are allowing us to really study in detail the development of these subsurface urban heat island beneath Chicago. Now, in this figure, you can appreciate how, with respect to the undisturbed ground temperature that can be found outside of Chicago and also in relatively undisturbed green areas in the city, the temperature that can be found in the ground beneath the loop, and here you have all these data points, is characterized by an offset. It's significantly higher. It's up to 11 degrees Celsius higher. And so these, like based on this data, we were able to assess the presence of a very significant urban heat island, subsurface urban heat island beneath Chicago. And again, it's not that something is particularly wrong about Chicago, but really it's the simple result of our presence and activity and our constructions. And so most of other cities worldwide suffer from the same phenomenon, if not more intense effects of subsurface heat islands. Now, in order to study more comprehensively this problem, what we did was to build a numerical model of the entire district under considerations. And so we leveraged monitor data to really model the heat diffusion from building basements and other underground infrastructures into the ground. And with the main aim of essentially trying to understand if without any calibration, we were able to get the temperature data that we can collect currently beneath the city. And so in this slide, I'm essentially showing you that yes, by simply considering the geometry of the loop and really the modeling of the heat that is dissipated into the ground from underground structures, we were able to capture relatively well the temperature that we can find currently into the ground. Here we have another snapshot of these temperatures, and specifically I'm showing you what was the temperature field in 1951. Essentially, after 1 year, the morphology of the loop was approximately similar, approximately equivalent to the one that we have today. Of course, new buildings have been built in the meantime, but they have been built arguably on the same footprint of previous buildings. You have the situation in 2022, so in recent years, and also the situation in 2051. And so really what we aim to do with these simulations was to study more in detail what happened in the past, what's the current situation, and what is likely to happen in the future. And as you can see, of course, like there were very significant temperature anomalies in the ground beneath the Chicago Loop. Darker is bad, and lighter it's okay. Essentially, the temperature in those locations it will be more undisturbed. And what you can appreciate is that the denser are the buildings, the darker are the colors you find. So the more significant are the temperature anomalies. And of course, there is a very significant influence of the urban morphology. Now, as I told you before, we know that materials and such as soils deform when subjected to temperature variations. And so as a part of this work, we were able to quantify, seemingly for the first time, the deformations of the ground caused by these temperature anomalies. Depending on the layer, we were able to assess that soil strata were expanding or contracting. And the results of these and other studies that together with my group I'm currently developing indicate that these ground deformations are responsible for vertical displacements exceeding tens of millimeters. And the reason why this is relevant is because we know as geotechnical engineers that displacements of that order of magnitude can be, on a case-by-case basis, problematic for the performance of civil structures and infrastructures, for geotechnical structures. In particular, they are unlikely detrimental for the performance of civil infrastructure at altitude limit states, but they can represent a problem for the performance of these structures at serviceability limit states. Because they can cause, they can be responsible for excessive settlements, especially differential displacements, tilting, and cracking. So essentially, we're not talking about the potential failure of structure because of this phenomenon, but we're talking about potential issues related to the durability, to the long-term durability and day-to-day operation, mostly related to the function and the aesthetics of structures. Now, because of all of this, so this has been an exploratory study. So as a matter of fact, we know more now, but we know still very little. So much more has to be done in the future. What is important is now to be aware of the fact that there is this silent phenomenon beneath our feet, and as a matter of fact, there is the need to mitigate it. Now, how? Essentially, one of the possible ways to mitigate subsurface urban heat islands is to absorb this waste heat. And this waste heat can be absorbed through so-called energy geostructures. As I told you at the beginning of this presentation, essentially, all kinds of earth contact structures that you can think of, such as the very foundations of buildings, retaining walls, slabs, tunnels, and so on and so forth, that can be turned into shallow geothermal heat exchangers. So into really elements that can absorb heat from the ground and can utilize this heat for space heating and cooling and hot water production. So essentially the concept of energy geostructures at this point is that earth contact structures become renewable energy producers. And now in this slide here, I'm showing you what in general we call energy piles or geothermal piles. So in black here, you can see the pipes, so plastic pipes that are mounted along the reinforcing cage. Within these pipes, there will be water and a little bit of glycol for operational considerations and operational reasons that will circulate into the loops and will enable to harvest energy from the ground, and specifically extract energy and inject energy depending on whether heating or cooling applications are targeted. In this slide here, you can see so-called energy barrettes or caissons, so very large foundations used to support tall buildings, energy slabs, energy walls, and energy tunnels as well. So really the message here is that any structure in contact with the ground can now be turned into so-called energy geostructures. And when dealing, for example, with tunnels, we now deal with massive sources of energy that not only can serve individual buildings, but can do that at the scale of entire city districts. Now, probably the only limitation of energy geostructures or traditional energy geostructures is that they were applicable only to new constructions. And so in order to overcome the challenge, together with my collaborators, we came up with a technology called EnerDrake, which is essentially a geothermal panel that can be attached in contact to any existing earth contact structure and turn it into a shallow geothermal heat exchanger. Really, the operational principle is the same as traditional energy geostructures, but the advantage is that through these panel, which is made of aluminum alloy and embeds a piping network, it's possible to harvest heat from already existing underground structures that represent 99% of the building stock, as a matter of fact. Here you have an idea of really what the panel looks like. So again, it's very thin. It's thinner than an inch. It can be attached in contact to any plane or curved surface, and then cosmetic panels can also be deployed on top of it to ensure optimal architecture integration, or as a matter of fact, to serve advertising. Now, what are the uses of energy geostructures? As I told you before, heating and cooling and hot water production, which represent, again, from 40 to 80% of the energy consumption of buildings. Energy geostructures can also be used for the de-icing of infrastructure, such as pavements, airport runways, and other types of civil infrastructure. They can be used for thermal energy storage. So essentially, these technologies can be used to use the ground as a thermal battery, with efficiencies that, based on our studies, can reach up to 70%. In the case of underground infrastructure such as tunnels, their thermal activations enables to reduce ventilation requirements. So essentially, as I told you before, what we can do is to absorb heat. We can absorb the waste heat that, for example, is released by trains braking and people traveling underground. And also, energy geostructures and infrastructures can be used to sell energy to district heating and cooling systems. So again, when you now deal with a parking garage, you deal with a multifunctional structure that not only can serve people, can let them park, can let them travel underground, but you're also dealing with a structure that represents a renewable energy carrier. It's a renewable energy source. So parking managers and operators currently become energy owners, and they can sell the energy. Now, these technologies can be applied in exactly the same way of traditional geothermal technologies in so-called ground source heat pump systems. So heat pumps are used to essentially enhance the energy input that can be taken from the ground with coefficients of performance that can range from 3.5 up to 6 and beyond in very favorable conditions. And really the advantage, I think, of energy geostructures compared to traditional geothermal technologies is that they harness structures that would be built in all cases. So they don't require additional drilling, and so they limit land use, something that cannot be done with, for example, vertical borehole heat exchangers. Because of these reasons, because of the fact that we can save, we don't need to drill specifically for the purpose of exchanging heat. These technologies are typically 20 to 30% cheaper compared to traditional geothermal technologies. And with return on investments that typically range from 4 to 15 years with an average of 6. So the payback period is relatively good. Of course, it varies across the world. In the US, it varies across the state in which you are, and depending whether there are tax credits available or not, but it's a fact that in general, it's something that can be very interesting. Now, all of this is good. Now, what are the challenges? Essentially, due to the fact that we integrate a heat exchanger into foundation systems and underground infrastructures, of course, we have energy-related challenges because we'll need to quantify how much energy can we harvest from the ground. We will deal with structural engineering challenges because temperature variations will be applied to the structures, and so they will deform. And we will also be dealing with geotechnical engineering challenges because of the thermal induced deformations that I was telling before. And so in this third part of the presentation, I will really touch base on a number of tools that, together with my collaborators, we have developed over the years to serve the analysis and design of energy geostructures. And most of these are, as a matter of fact, summarized in the book that I had the opportunity to write together with Professor Louis from EPFL. Now, to highlight a little bit the differences with respect to traditional heat exchangers and traditional geostructures, I would like to mention that with respect to the heat and mass transfer phenomena, a key difference is really the geometry. The geometry of energy geostructures, irrespective of whether we consider piles or, for example, energy walls, is their geometry. We have a number of heat transfer modes, convection, conduction, and that can be developed in the pipes, in the concrete, in the ground, but also in the case of underground infrastructure such as parking garages and tunnels, we also deal with convection with the air. So as I told you before, we can harvest heat not only from the ground, but also from the air when it's present adjacent to a given underground structure. Now, with respect to the behavior of these technologies and compared to traditional geotechnical systems, the main difference is that if traditional geotechnical systems were subjected only to mechanical loads, energy geostructures are also subjected to thermal loads, which lead to a completely different behavior and a completely different response. And so when I started to work in this field, and even before that, my peers in the community, there was very little, like we knew very little about the behavior of energy geostructures. And so over the years, there have been various developments in terms of tools to really serve the analysis and design of energy geostructures. Currently, we have charts that are available for this purpose, analytical models through which we can model energy geostructure in a relatively comprehensive way and robust way. And then, of course, there are numerical models that are the most rigorous and comprehensive and thorough approach that can be used for this purpose. But of course, these tools come at the expense of significant resources in terms of time and expertise in order to be carried out. Now, irrespective of the methods that are used, the message that I would like to convey is that at the end of the day, from an energy perspective, the challenge is to quantify how much energy and power can be harvested from the ground. And from a geotechnical and structural engineering perspective, the challenge is to quantify the significance of these temperature variations, and that will need to be considered in the design and serviceability limit states of these technologies. So, as a matter of fact, energy geostructures, like all geothermal technologies, will apply temperature variations into the ground. but they will be generally more limited. And in any case, their operation will allow us to absorb, for example, the heat that comes from subsurface urban islands that was mentioned before. Now, in the following, I will touch base on the main features of these of the tools, of some of these tools that have been developed over the years, starting with charts. And essentially, the idea of charts is to have schematics, like quantitative data sets that enable us to quantify for given geometries, site conditions, and so on and so forth, what are on the one hand, so what is on the one hand the energy and power that can be harvested from the ground, and on the other hand, what are the effects on from a mechanical perspective, what are the effects on the structure and the ground. And so there are currently charts available for piles and barrettes, walls and slabs, and tunnels. These are only a few of all of those that have been developed by my team and many other colleagues and peers in the community. But really, the overarching aim of all of these charts is to serve estimates, quantitative estimates that can still be rigorous. In general, they can provide us with values that can be plus or minus 20% accurate of what will eventually be found in practice for use in analysis and design, at least in schematic analysis and design. Then there are analytical models, and so really the main advantage of analytical models is that they can be more tailored to the actual site conditions and characteristics of sites. And over the years, there have been a number of models that have been developed. Here, I will touch base on three main models that have been developed by myself and my collaborators. The interaction factor method to describe the mechanics of energy pile groups and really account for group effects. The extended Winkler analysis for energy walls and slabs, and also recently we're working on an extended cavity expansion analysis. So really here the aim is to take some of the most fundamental solutions in mechanics and geotechnical engineering and extend them to non-isothermal conditions in order to be able to consider the influence of temperature variations. Let's start with the interaction factor method to really analyze energy pile groups. The method is quite simple and essentially resorts to the quantification of the so-called interaction factor between a pair of piles that can be identified for any pile group. And this interaction factor is essentially a coefficient that depends on the spacing, depends on the geometry of the problem and other features, and is defined as the additional displacement due to an adjacent pile over the displacement of a single isolated pile. What we can do with this approach and the elastic principle of superposition of effects is to really calculate what are the interactions between any piles in a group and eventually determine what is the overall group deformations caused by not only mechanical loads, but currently also thermal loads. In order to define the interaction factor, we specifically extended two analytical models that really allow us to quantify how much piles will deform due to the loading and presence of neighboring piles. And eventually what we can get are results like this, where so we can really simulate, as you can see quite well, the values of vertical strain or vertical displacement at the head, for example, of these foundations. And you can see that essentially for a larger number of thermally activated piles, the group deformations increase. And this is exactly the rationale for having a method like this one to really study group action and effects for analysis and design purposes. In order to address the analysis and design of energy walls and slabs, what we did again with my collaborators was to extend the classical Winkler solution to non-isothermal conditions and really use this basic solution to analyze one elementary unit in much the same way we did previously with the interaction factor method, to then be able, with the elastic principle of superposition of effects, to model and simulate the behavior of more complex plane geometries, such as, for example, cut and cover tunnels. And so what can be done with this model is like our predictions like this. Essentially, for any given underground structure, plane and underground structure, we can, for example, quantify the influence of the thermal activation of one element on the other elements in terms of internal actions such as bending moments, shearing forces, normal forces, and so on and so forth. And in turn, then we will be able to consider these thermal induced effects in the design. When we come to tunnels, and this is in work in progress, what we're doing is to extend the cavity expansion analysis and the cavity expansion theory to really account for temperature variations applied to these underground structures, with the aim of being able to calculate radial stresses, hoop stresses, and displacement caused by temperature variations. Now, as I told you before, the most rigorous approach are numerical models. So these are the most rigorous approach to really simulate, analyze, and design energy geostructures. There are a number of formulations that can be used for such purpose, but essentially what these approaches allow us to do is to model the heat transfer, mass transfer, and deformation phenomena that occur in the subsurface. And I will not go in very specific details of this, but rather I will focus on a number of applications that have been designed with these latter types of methods by my collaborators at GeoEg. And so I will kick off with this example that represents a tower under construction that will be powered by geothermal energy. It's an office tower for which the foundation systems were thermally activated. The foundation system is specifically composed of barrettes, slabs, and walls. And essentially what numerical models allow us to do is, as I showed you before, to reproduce in detail the three-dimensional geometry of these underground construction, consider their thermal activation, and really study over time what is going to be the energy and power that can be harvested from the ground, and what are the thermal induced stresses, deformations, and displacements that will be caused into the structure. Here you can see other cross sections of what happens during the building heating season or the building cooling season, but it is clear how, due to the thermal activation, these structures deform. And so really the game here is to be able to harness the maximum possible amount of energy from the ground while imposing the minimum possible temperature change, or in any case, a temperature change that is compatible with the performance of these structures. As a second example, I would like to share this other one that represents a mixed tower currently under construction in Switzerland, that again, whose foundation was again thermal activated to contribute to the thermal energy needs of the building. We specifically deal with thermally activated slabs and walls. And again, in this case, numerical models enable us to simulate in detail the performance of these structures for even very long time frames of 50 years and beyond, which are typically required by standards as design lifetimes. From theory, we can then go to practice. So here you have a snapshot of what the application of the pipes at the construction site looks like compared to what was initially foreseen. So of course, there can be a number of differences, but overall, good installation practices will ensure that these technologies will function well. Here again, you have two other pictures of this installation, and really, as you can see, you are dealing now in construction sites with kilometers or miles of pipes with water circulating to them, and that water essentially enables you to absorb heat from the ground, or to inject heat into the ground if you do cooling, for example, building cooling. Now, to conclude this presentation, I would like to convey three main messages. The first one is that subsurface urban heat islands, also called underground climate change, represent a silent hazard for civil structures and infrastructures, and so more work is deemed necessary in the future to really assess where and to which extent this can be the case. At the same time, though, I hope I was able to convey the message that this phenomenon represents a massive opportunity, because we can absorb very substantial amounts of waste heat from the urban underground on top of geothermal heat. And energy geostructure, as a matter of fact, represent one of the possible solutions, but a very cost-effective one, that enables to do this while supporting our structures and infrastructures. With this, I would like to thank very much the sponsor of the research work that I presented, again, all the help of my collaborators and colleagues, and of course, the GI and Keller for the wonderful opportunity of presenting my work in this sustainability webinar series. Thank you, and I'm happy to answer any questions.
Well, that was outstanding. Thank you very much, Alessandro. Please, if you do have questions, put them in the chat in your video there. I'll start off with a couple. Do we need to change the design of energy geostructures compared to traditional Earth contact structures?
Yes. So the short answer is yes. As I mentioned in the slides, the influence of temperature variations needs to be considered in design, not at ultimate limit states. So temperature variations resulting from the geothermal operation of these technologies do not involve ultimate limit states, but they can affect serviceability limit states. So we're talking about problems related to deformation, but really, rather than re-envisioning and restructuring completely the design, we simply need to perform a few checks. So typically we need to control compressive stresses, tensile stresses. We need to limit these effects. We need to limit deformations, deflections, and so on and so forth. And to date, even like in practice, there have been very few cases, I can count them on a few fingers, of designs that needed a change. And so in those cases, also solutions can be to change the class of concrete or increase the reinforcement and so on and so forth. So there are solutions. But so in short, yes, it needs to be, the effects of temperature variations need to be considered in design.
Excellent, thank you. This one from our very own Kimberly Martin, Kmart, as we like to call her. Do we think that underground climate change is happening in warmer cities than Chicago? Is anyone measuring it?
So there are various measurements from different cities across the world. So I would argue, although I don't have data for that, that essentially, again, as I mentioned, as soon as we build a construction, some heat will dissipate into the ground. Then the question is how significant that is. Now, in warmer climates, it will very much depend. So warmer climates will be characterized mostly by cooling needs. Then really the question is where the machinery that is used to cool down those buildings is put. Oftentimes it's put in underground structures, and that machinery rejects heat. And so that heat can go into the ground. So in the US currently with my team, we're looking for data. There are not many data beyond New York City, Chicago, and a handful of other cities. There are though data for European cities, so more knowledge is needed, but I would argue that yes, temperature anomalies will be present also there.
Excellent. This question from Mr. Mike Mahood. What materials are the exchange pipes made of embedded in concrete?
Yeah, typically they're made of polyethylene, plastic, essentially. Then they are more elaborate plastic materials, and there are also standards for these materials that ensure durability over the lifetime of these applications and so on and so forth. But it's something relatively simple. It's low-tech hardware, I would argue.
This one from Praveen Kumar T. Is the temperature variation high enough to convert the water to steam?
No, no, absolutely not. So in geo-exchange and shallow geothermal, we deal with relatively limited temperature variations of the order of 5 degrees in most cases. It depends on the heat pumps, it depends on the applications, 5, 10. When we deal with thermal energy storage, we can have larger temperature variations, but no, essentially we cannot convert water into steam. Yeah.
Excellent. This one from Konstantinos Severis. Does lowering ground temperature increase heat transfer between the crust and the lithosphere?
That's a hard one. Well, since with geothermal technologies, we will cause temperature variations in the subsurface, and we will have a gradient, then we will have also heat flowing. But so there will be an impact. As a matter of fact, these technologies cause an anomaly in the underground, but as long as that anomaly is controlled, it doesn't represent a problem. So for example, there are, again, standards and regulations from environmental perspectives that need to be met. So temperature variations need to remain within a given window. So all of that can be controlled.
Thank you. This one from Omar Keza. You mentioned the use of energy structures as thermal energy storage. Can you provide an example of how the heat can be stored in such structures?
Yeah, absolutely. So really, the concept of using energy structures as thermal energy storage systems is the same as the concept behind more traditional underground thermal energy storage systems, such as packet bed, like essentially tanks filled with sand or beads that can be used to store heat into those reservoirs. If you now deal with a pile, you have a system that essentially is also similar to some extent to borehole heat exchangers. So what you can use is the piles as heat transfer media to store heat into the ground. So essentially the aim is to create, if you want, a bubble of heat around the foundation. What you will do is that you would couple the system with solar thermal panels in most of the cases. So you will inject heat during summer and you will reuse that heat during winter. Or you could do the opposite. You could actually store cooling energy during winter and reuse it during summer. And but really the aim is to store heat in the ground and reuse it later on. Of course, a very important aspect in those applications is the presence and significance of groundwater flow. If you have groundwater that flows, it could drive all the heat away. So attention needs to be paid in those conditions. Yeah.
Excellent. Carlos, I love this one. Carlos Fuentes asks, what percentage of the energy use of a building, heating and cooling, can be achieved with these systems?
So theoretically speaking, up to 100%, even more. Now, is this the solution to all the thermal energy needs of the Earth? Absolutely not. So I hope I was able to convey the message that essentially it's a game between surfaces. We need to we need to provide heating and cooling to a given surface above the ground. And we deal in general with a given surface like that can be thermally activated underground. So of course, when we deal with very high-rise buildings, we will have deep foundations, but it's very likely that compared to the surface that we have above the ground, the available surface that we can thermally activate will be limited. So in those conditions, maybe we will be able to meet 20%, 30%, or even less. But in other situations where, let's say, these surfaces are more balanced, we can meet 60, 70, 80% and more. Although I would say that even if we could meet 100% of the thermal energy needs, we would probably not do that with geothermal technologies, because geothermal is renowned to be a good energy source to meet a base load. But then in order to meet peak loads, it's preferable from an efficiency perspective to use other technologies and other renewable energy sources. But so theoretically speaking, again, coming to the question, energy geostructures, like other shallow geothermal systems, can meet up to 100% of thermal energy needs of buildings.
Thank you. This one from Sang-Ho Lee. Have you ever measured thermal capacity conductivity changes by groundwater level at above or at below? And how much change between dry soils and wet soils?
So the changes can be quite significant. So if you consider a sand, for example, the thermal conductivity of a saturated sand can be of 3 watt per meter Kelvin or even more, whereas the thermal conductivity of a dry sand can be of 1.5, can be half of it. So really the presence of groundwater can play a very significant role on the thermal conductivity and thermophysical properties of soils and rocks in general. I would say, though, that even if the thermal conductivity is low, these systems will work and will be able to provide some amount of heat. So really the question will be how much and at what cost. But a priori, it's not that these systems and technologies will be inapplicable, for example, in dry conditions.
Oh, excellent. So from Jay, excellent presentation. Thank you. How commercially viable are these systems? Can these be adopted on routine residential projects? And how much do they cost for a new build or to retrofit existing homes?
Yeah. So they are, let's say, quite ubiquitous. It depends on the region across the world that you consider. So I would say shallow geothermal technologies and energy structures are quite common nowadays in Europe, especially. They're becoming more and more common in the United States. And as I mentioned in the presentation, the payback period is typically of 6 years on average. Again, it depends on the size of the structure, it depends on a number of variables, but it's quite reasonable. Yes, they can meet the thermal energy needs of residential buildings, but really the rationale for thermally activating pies only, slabs only, walls only, or all of the above will be case specific, but yes.
Thank you. This one again from Konstantinos. Are there studies showing the distance/rate the heat travels through soil off of underground structures?
So can you say that again? Are there studies?
Yeah, let me
Sorry for that.
Are there studies showing the distance/rate that heat travels through soil off of underground structures? No worries.
Yeah. So there are, as a matter of fact, this information can be gathered from the very many publications that are available on this topic. But to give a direct answer, we can talk about several meters and more, let's say. I would even say beyond 10 meters and 50 meters. Of course, it depends on the timeline that is considered. If we consider a geothermal system after 1 year of operation, the zone of the ground affected by temperature change will be relatively limited. If you consider the same system after 50 years, especially if you're dealing with an unbalanced energy operation, the temperature anomaly will be more significant. But so we can deal with quite significant thermal interactions. And for these reasons, in some countries around the world, there now is the interest in working on standards to limit thermal interactions between neighboring buildings, because there is a question of, now the principle of who comes first is best served doesn't apply anymore, because if today a private person builds a building and starts to harvest heat, and tomorrow somebody else comes and builds another geothermal systems, they will actually steal the heat from each other. So there will be regulations that will come into play soon.
Wow, like thermal boundaries and thermal
exactly
ownership. Yeah. Interesting.
Yeah.
This one from Vishnu Dialogy, pardon me. The process may be important to the de-icing of culverts. Is this a possibility, or has it been already addressed?
So today there have been a number of de-icing applications, mostly for the decks of bridges and airport runways. But theoretically speaking, so in principle, every surface can be de-iced. So yes, yeah, it will be again a matter of with which return of investment, with which power, and so on and so forth. But these things can be assessed on a case-by-case basis.
Thank you. This one from Patrick Mans. What are the most ideal? I love this. What are the most ideal soils for this system to work best?
There is and there is not, but I would say a saturated soil is certainly better than a dry soil. The more conductive the soil, the better it will be for heat extraction and injection. And of course, if there will be groundwater flow, it will also be a plus, because that will enhance the amount of heat that can be exchanged by advection. So not only we will be able to leverage conduction heat transfer, but also advection heat transfer. But as I mentioned before, if in those situations we target underground thermal energy storage, that will actually represent a problem. So
right, you're washing all your heat away.
Exactly. Yeah.
Kind of like grouting.
Yeah, exactly.
Thank you. So this one again from Kimberly. What kind of additional preliminary tests should be done when considering if energy piles are good at a good solution at a site?
I would say that the extent of in situ testing campaigns really depends on the size of the project, but for at least based on my experience, for projects of an installed capacity of exceeding 10 kilowatts, the test that needs to be performed in general is the so-called thermal response test. That essentially is a test that allows us to quantify the effective thermal conductivity of the ground and other parameters the undisturbed ground temperature and the thermal resistance of the heat exchanger to really understand what's the geothermal potential of the site. So that is the test to understand really the geothermal potential of a site. Then, depending on the sensitivity of the soil strata and so on and so forth, there can be other geotechnical tests that might be needed, but it's very case dependent. But I would say the test that is needed, especially for a large project, is the TRT, thermal response test.
Wow, I can see this becoming a new industry, thermal testing. This question, I think this is going to be the last one, folks, is from Omar Keza. Can hollow section concrete pile foundations be thermally activated? If yes, yeah, where can we place the heat exchange? Do we need to put it in the concrete shell, or we can put it in the hollow?
Either or both. So as a matter of fact, some of the very first thermally activated piles were actually hollow. So they were precast. And so the pipes can be put in most of the cases, they're put inside, so in the hollow space that then is filled either with sand or bentonite or any other filling material or water, and really can be used as a heat transfer mean. Mm-hmm. In principle, they could also be embedded in the wall, but it's more rare, I would say. But so also hollow piles can be thermal activated. Yes.
Outstanding. Thank you. Thank you very much from all of us. This has been a wonderful presentation. Great series of questions, everybody. Thank you for your participation and attendance. A few housekeeping things. We are offering a PDH for this. Please just reach out to me saying you would like one. Let me know what state you are in. There's about 8 states that we need to go through some other procedures to get you your PDH. But otherwise, please feel free to email me and we'll get those sent off in the next 6-8 months. We have to send away for them and have them engraved.
Thank you again.
Thank you.
I like the idea of engraving for the PDH certificates. Alessandro, that was fantastic. Thank you for doing that. And the number of questions, it's usually hard to get people to ask questions in a live stream. So thank you for a really engaging presentation that I think, I always say, I favor the things that people could walk in off the street and get something out of that you don't necessarily have to be a PhD for. And this one, I think, falls into that category, despite the equations. There were some equations, but I do think that if anyone watched this, they would have a lot to take away. So thank you. We really appreciate that. For all the viewers, thanks for your questions, especially, even if you didn't ask a question. Thanks for being with us today. I put in the chat that we will have the final episode of the Keller Sustainability Series, not in August. I'm going to take a month off, relax, maybe go to the beach, do something else. We'll have the final episode on September 17th at 2 p.m. Eastern Time. You can get more details. Well, you're going to get it in an email, whether you want it or not, from me, but you can also get it on our Eventbrite page, and you can find out information about all of our upcoming live streams there. The next live stream that we will be doing is 1 week from right now, 2 p.m. next Tuesday. It'll be Kyle Rollins' second of 3 live streamed cross USA lectures. You will want to be around for that one. It is going to be great. We have much more coming up throughout the rest of the summer in this GI Summer of Live. And of course, if you liked what you saw today, click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. So Alessandro, thanks again. Great topic, great presentation.
Thank you.
Tim, great job moderating as always. Our producer today was Matt Roberts, and we will see everybody very soon.